All right, this is the second part of the additive solution video. And so this is a similar situation where we're again adding solutions together, but the question here is a little bit different. So first, to draw my picture, I think it's just helpful. In this case, we have a 0.25 molar cobalt chloride solution, and I have 50 mils. And my second solution this time is not cobalt chloride, but it's nickel chloride, different molarity. And I have 25 mils of this solution. Again, we're going to add them together to create a new solution. And this time I'm being asked, what's the molarity of each ion in the final solution? And so I think there's a couple things that you have to think about. You first have to consider, is there going to be a reaction in this case? Because if there is, that would change who's in this solution. Now, in this situation, if you tried to take cobalt chloride and nickel chloride and react them in a double replacement reaction like they would, you would get the same products because you have that common ion of the chloride. So there is no reaction in this case. Really what you're just dealing with is the fact that both of these substances are ionic. They're going to ionize, and they're going to ionize completely. And so there are 3 ions in this solution, and they would be the cobalt ion, the chloride ion, and the nickel ion. And we'll talk about how much of those ions is present or are present in this final solution, because that's really important in this problem. So if that's what I'm attempting to solve, then at the end of the day, I am going to need 3 molarity calculations, and I'm going to need the molarity of the cobalt ion, I need the molarity of the chloride ion, and I need the molarity of the nickel ion. Of course, when we find molarity, it's moles per liter. And in this case, if I'm looking for the molarity of the cobalt ion, then I only need the moles of the cobalt ion. If I'm looking for the molarity of the chloride ion, I only need the moles of the chloride ion. And if I'm looking for the molarity of the nickel ion, then I only need the moles of the nickel ion. We have to keep our apples and apples together, so to speak. And so now I can go about thinking about this calculation. The easier part of all of these calculations to determine is the volume, because again, volume is additive. So if I mix my 50 with my 25 mils, I end up with 75 milliliters, which is 0.075 liters. And that's going to be the same for all 3 situations because they're all 3 in the same container. But now I need to think about my mole calculations. And so to determine moles, I'm going to have to go back to my 2 original beakers. And so in the first beaker, I have a molarity and I have a volume, which means I can calculate moles of the cobalt chloride, the entire substance, by using the same formula that I'm used to, molarity times liters. My molarity was 0.25. My liters were 50 mils, so 0.05. And that gives me a molarity of 0.0125. Sorry, moles, those are moles. Keeping in mind that that's moles of the whole entire substance. That's moles of COCl2. I'm not really interested in that because I'm interested in the moles of each ion, but we'll take that into consideration in a minute. I'm going to do the same thing for my second container to find the moles of the nickel chloride by taking its molarity times its liters, so 0.35 molar in the second container, 25 mils, or 0.025 liters, giving me moles of 0.00875, and again, that's moles of the entire substance. And I'm not really interested in that, except I am interested in how that relates to the individual ions. And so this is the part that deals with ionization. We know both of these substances are ionic. They will ionize, and not only that, but they ionize completely. The cobalt chloride ionizes into CO plus 2 and Cl minus 1, but we get 2 of them. And the nickel chloride does the same thing. It ionizes into nickel plus 2 and 2 Cl minuses. Now that I have my moles of both whole substances, I can use my sequences to figure out the rest. If this is 0.0125, this is also 0.0125, and the chloride ion moles are, of course, double because of the 1-to-2 ratio. We can do the same thing with the nickel chloride and play the same game, saying that this is a 1-to-1-to-2 ratio. And now at this point, I have all the numbers that I need because I have all the mole values. If we go back up to the very beginning and think about that, the first calculation I want to do is the moles of the cobalt. The moles of the cobalt came only from the ionization of this, and so my moles of cobalt are 0.0125, and that will give me enough information to calculate its molarity. I'll skip the chloride ion for just a second. Nickel comes from the nickel chloride, and it gives me a mole number of this. And I have enough information at this point in time to calculate the molarity of the nickel ion. The chlorine is interesting because the chlorine comes from two places, and the chlorine comes from the ionization of the cobalt chloride, but also the ionization of the nickel chloride. And so knowing that the chlorine moles are coming from two different places, I need to take those two numbers and add them together to get the total moles of chlorine. And now I have enough information to solve this problem. So I just have to do my calculations. The molarity of the cobalt ion ends up being 0.167. The molarity of the chlorine ion ends up being 0.567 molar. And the molarity of the nickel ion ends up being the smallest of the three, 0.117 molar. And so that's how we can deal with calculating concentrations when we mix solutions together.